So I want to start today with a bit of a warning.
Oh,
Yeah, and this isn't even my warning. I'm literally reading this from the first slide of our source material.
the trigger warning.
That's the one. It says, and I quote, "The next topic could lead to momentary panic." And, I kind of get it.
Yeah, because we're being asked to do something that, well, it feels pretty unnatural now in 2024.
Completely. It's asking us to abandon the mouse.
To let go of that safety blanket. No more colorful icons, no clicking next.
Nothing. We are talking about the raw, unfiltered command line.
It's a big jump.
It is. We're diving into the intro material for a course called CS123, System Administration. And the whole mission is about moving from being a user to an administrator.
And that's such a key distinction. A user is passive. You sort of accept the computer as it's given to you.
Yeah.
But an administrator, they define the reality of that machine. They control everything, the resources, the access.
But to get there, you have to strip away the interface. You have to understand how the computer actually works from the silicon up.
And our guide for this, the instructor, he has a pretty interesting background.
He really does. I was looking at his bio, expecting, the usual. Computer science degree, maybe some time at a tech company.
And he has that.
He does. BS and MS in computer science, consulting. But right at the top of the list, music education.
I actually love that. It seems random at first, but if you think about what an operating system does.
You mean the idea of orchestration?
Exactly. Music is all about timing and structure and managing different parts so they don't all clash.
That's a great way to put it.
And that's basically the job description for a system administrator. You've got all these programs screaming for attention, and you're the conductor.
So he's not just debugging, he's keeping the rhythm. And speaking of rhythm, he goes on this little brief aside in the intro about a hobby project. Did you see the photos of the PDP-10?
The nerd cred section, yes.
This wasn't just like, I built a PC. This was, I built a 1960s mainframe replica with a soldering iron.
The photos are amazing. It's just bags of resistors and LEDs all over the place.
It looks so complicated, like he's defusing a bomb in a movie. But no, he's building a kit for a PDP-10.
And that specific machine is so important to computing history.
Why that one in particular?
Well, the PDP-10 is, it's royalty. It's the machine that really powered the development of the ARPANET.
The precursor to the internet.
Exactly. So his point is really deep here. To understand the cloud today, you have to understand the roots. You have to understand the metal.
The physical reality of it.
Right. We just click a button and spin up a server now.
Yeah.
It feels like magic. But at the bottom of it all, there's still electricity moving through a resistor. He's grounding them in that physical architecture.
Which has a name that comes up a lot, John von Neumann.
The von Neumann architecture.
Yeah.
And it's wild. It was proposed in 1945, and the basic blueprint is still in your phone right now.
So what is that blueprint? Like, what are the absolute core parts?
It's basically a trinity. You have the CPU, the central processing unit. That's the brain. Then you have the memory unit, where the data lives while it's being used. And finally, input and output devices.
The brain, the memory, and the mouth and ears.
You could say that.
Yeah.
But here's the problem. The components on their own are just dumb. They're powerful, but they don't know what to do or when to do it.
So you need the conductor.
You need the operating system, the OS. The course calls it the hardware orchestrator.
I like that term. It's better than just Windows or Linux. It describes the actual job.
It really does.
Yeah.
The OS decides everything. Who gets to write data to the disk? How are errors handled? Who gets the CPU's attention?
There's a note in here that an OS is tied to specific hardware, which I found a little confusing at first.
It seems like a paradox, right?
Yeah.
Because you can install Linux on so many different machines.
Yeah.
But at its core, the OS has to speak the literal electrical language of the hardware. It uses things called drivers to act as translators for all the different parts. But yeah, the OS is intimate with the metal.
Okay, so if the OS is the boss, what are its main departments? The course outlines these big four concepts.
These are the four pillars.
Let's run through them. First up, booting.
The Genesis moment. You hit the power button, the hardware wakes up, and looks for the BIOS.
Basic input-output system.
Right, and the BIOS is just smart enough to find the next link in the chain, which is the bootloader.
And the bootloader's job is to find the kernel.
It's a relay race.
Uh-huh.
And once that kernel, the core of the OS, is loaded into memory, the system is officially alive.
Which brings us to pillar 2, process management.
So this is the to-do list for the system. Every single thing running your browser, the clock, a background service, is a process.
And each one gets a number, a PID.
A process identifier, yep. And the OS just juggles them.
Because the CPU can only do one thing at a very specific instant, right?
Exactly. It's more like speed dating than multitasking. It gives one process a nanosecond, pauses it, saves its state, and then moves to the next one so fast that it looks like everything's happening at once.
And if a process just freezes up,
The OS can kill it.
kill the process. It sounds so aggressive.
It has to be. If one program goes rogue and hogs all the resources, the orchestrator has to step in and cut the mic.
Okay, pillar 3, memory management. This is where it gets into something called mapping, and honestly, it sounds like the OS is lying to the programs.
Well, it is, but it's a benevolent lie.
Explain that.
So you've got your physical RAM. It's a messy place. Data is scattered all over. A program doesn't want to deal with that mess.
It just wants a clean workspace.
Exactly. So the OS creates virtual memory. It says to the program, here's a perfectly clean, empty block of memory just for you, from address 0 to 100.
But in reality,
The OS is taking the program's data and sticking it wherever it fits in the real physical RAM. It just keeps a secret map so it knows where everything actually is.
why do that? Why not just show the program the real RAM?
Security. That's the main reason. If a program could see the real memory addresses, it could maybe start peeking at what other programs are doing.
So it couldn't steal passwords from my browser.
Precisely. The OS keeps every program in its own padded cell. They can't see or touch each other.
That makes perfect sense. And it's a great segue to the 4th pillar, security.
Right. Because in a system like Linux, which is designed for many users, the #1 rule is boundaries. You can't touch what isn't yours.
And speaking of Linux, we have to talk about its core philosophy. This mantra that's repeated in the slides. Everything is a file.
That is the single most important concept in the Unix and Linux world.
But it's weird. I get that a document is a file, but a directory is a file.
Yep. A directory is just a special file that contains a list of the names of other files.
Okay, I can sort of wrap my head around that, but then it says devices are files, so my keyboard is a file.
For the OS, yes. Your keyboard is represented as a file in the system. When you type, you're writing to that file. When the OS reads your keystrokes, it's reading from it.
Even my monitor.
Your monitor is a file. Sending data to it makes pixels light up.
Why? Why abstract it that way?
Because it makes the tools universal. If everything is just a file, you can use the same simple commands like read and write to interact with a document, a hard drive, or a network connection. It unifies the whole system.
So everything just hangs off of that one single root directory.
The / the trunk of the tree.
But that brings us back to security. If my keyboard is a file, how do I stop another user from just reading my keyboard file and logging my keystrokes?
That's where permissions come in. This is the bread and butter. Every single file has 3 layers of access control.
The honor, the group, and the world.
Right. Though the slides point out that world is a bit dramatic, it really just means everyone else on this system.
And for each of those 3 layers, you have 3 permissions you can set.
The Trinity. Read, write, and execute, or RWX.
Read and write are obvious, but execute is interesting. In Windows, an .exe file just runs. But in Linux, a file isn't automatically runnable.
Correct. You have to explicitly grant the execute permission. It's a safety feature. If you download a script, it won't run by accident. You have to consciously flip that switch.
Okay, so we have the theory, the architecture, the pillars, the philosophy. Now, for the part that causes that momentary panic, actually using it.
The fear factor.
The rule in the course is no mouse, you log in, you are in the terminal. Why be so strict about that?
The instructor calls it avoiding automation complacency.
Unpack that for me.
When you're using a mouse, you are a consumer. You can only click the buttons the developer gave you. If there's no button for what you want to do, you're stuck.
But in the terminal?
In the terminal, you're speaking the language of the OS directly. And crucially, text can be scripted. You can't script a mouse click very easily, but you can write a one-line command to rename 5,000 files in an instant.
So losing the mouse is the price you pay for the power of automation.
That's it exactly. The goals are speed, consistency, and error detection. A script does the exact same thing perfectly, 1,000,000 times.
So let's picture it. You've booted up, you're in the shell. It says we're using bash.
The born-again shell. It's a classic programmer pun.
And you just see a blinking cursor. Nothing else. How do I even know where I am?
You have to ask. The very first command is pwd.
Print working directory.
It tells you your exact location in that huge file tree. Usually starts you in your home folder.
And to move.
cdd change directory.
Yeah.
You just give it a destination. And if you ever get lost, cd. The tilde character is your shortcut back home.
Okay, I'm home. I know where I am. Now I want to see what's in the room. Type Ls.
List. But that just gives you names. We're admins now. We need details. So you add a flag, LSL.
The long output. And this is where the screen fills with that cryptic text. That RRW stuff.
It looks like code from the Matrix, but it's actually very, very structured.
Okay, so walk us through that first string of characters.
The very first character tells you the type. A dash means it's a regular file. AD means it's a directory. Simple.
And the next 9?
That's your permissions grid. They're in sets of 3. The first 3 are for the user, the owner.
So RWX means I can read, write, and execute it.
You have full power. The next 3 are for the group. Maybe they only have RX, so they can read and run it but not change it.
And the last 3 are for everyone else.
Right. Maybe they just have R. They can look, but they can't touch.
Wow. So in one single glance, LS.boolean tells you the type, the permissions, who owns it, how big it is, and when it was last modified.
It's incredibly dense with information. A graphical icon tells you almost none of that.
There's one more LS trick in here that I thought was cool. Hidden files. The L is a command.
The all flag.
In Windows, hiding a file is this whole process. How do you hide a file in Linux?
You start its name with a dot.
That's it, just a period.
That's it? If a file is named .config, a normal ls won't show it to you.
Is that actually secure?
Not at all. And the slides are clear about that. It's not for security. It's for tidiness.
Yeah.
Your home folder is full of configuration files, the plumbing. You don't need to see them all the time.
So it's just to keep them out of your way.
Right. And LSM reveals all of them. It's like lifting up the rug.
Okay, so if I'm in the terminal and I forget everything we just talked about, what do? There's no help menu to click.
No, but you have something even better. You have man.
The manual.
You type man, followed by any command.
Yeah.
Man ls.
Yeah.
And it opens the full manual page right there in your terminal. It's a self-contained encyclopedia.
That seems to be a theme. The whole system is self-contained.
It is. That's the beauty of it.
So, stepping back for a second, we've gone from a soldering iron and a PDP-10 all the way to the LTIL command. What's the big takeaway? Why go through this momentary panic?
I think it comes down to a word the instructor uses a lot. Intuition.
Intuition.
Look, if you just teach someone to click a specific button to solve a problem, they only know how to click that one button. If the button moves in the next update, they're lost.
They have no model for what's actually happening.
Exactly. But if you understand that a process is a PID that the kernel's managing, or that a file is just bytes with permissions, you don't need the button. You can figure out on any system because you have a mental model of how the machine thinks.
It's the difference between memorizing a phrase book and actually learning to speak the language.
Perfectly put. And once you speak the language, you can automate. You stop working for the computer, and you make the computer start working for you.
From user to admin.
From passive to active. It's a power shift.
I want to leave everyone listening with a small challenge. We've talked about the fear of the terminal, but pretty much everyone has one on their computer right now.
Terminal on a Mac, PowerShell, or WSL on Windows.
Just open it up, type LSLR if you're in a standard Windows prompt, and just hit enter. Don't worry about understanding it all.
Just look at the text.
Yeah. See if you can spot the permissions. See if you can find a D for a directory. Just peel back that curtain a tiny bit.
See what's really going on under the hood.
Exactly. Thanks for taking this deep dive into the command line with us.
Anytime. See you next time.